Welcome back to the lecture number 2 of fluid mechanics. In this lecture, we are going to talk about different properties of fluids. These properties of fluids are very important and we should know them because by knowing them, we can determine the behavior of fluids. Also, these properties are used in derivation and several numerical problems. So, without knowing these properties, we cannot judge the behavior of fluids and its related concept. So, it is better to understand these properties. These properties are mentioned over here. These are the first one is density, the second one is weight density, the third one is specific gravity, the fourth one is surface tension, fifth one is capillarity, and sixth is viscosity. So we will discuss each of them in detail one by one. So starting from density. Density is also known as mass density and is represented as rho. So density is defined as mass per unit volume. What does this tell us? So this was a standard definition of density. So what does it tells us that how much mass is available per unit volume, and it shows the compactness of material, that how much the material is compact. For example, if you have two materials A and B having density rho A and rho B, if density of A is high and density of B is low, so it means that there is more mass of A is present per unit volume as compared to the mass of material B per unit volume. So again, if density is high, so it means that more mass will be present per unit volume and that will be dense medium, or you can say that it is dense material. Same is the case if your rho or density is low, so it means that less mass per unit volume, so material is less denser. So what will be the SI unit for density? We know that density rho is equal to mass per unit volume, so the unit of mass in SI will be kg, while the unit of volume is cubic meter. So the density unit in SI system or SI unit is kg per cubic meter. Now for CGS system, that is centimeter gram second system, we have unit of density will be equal to, that unit will be gram, mass unit is in gram, and volume unit will be in cubic centimeter, or we can also say that it is gram per cc. Cc stand for cubic centimeter. Now density of water, which is also equal to rho of water, and that rho of water is 1000 kilogram per cubic meter at 4 degree centigrade. Remember that this density of water is 1000 kilogram at 4 degree centigrade. Below or above this temperature, the density will be changed. Why this density will change? Because we know that due to anomalous behavior of water, its density will be changed. So at 4 degree centigrade, the density of water will be 1000 kilogram per cubic meter. Now we will move towards second property, that is weight density. This weight density is represented as gamma, and this weight density is defined as, let me write, weight density is equal to weight per unit volume. Weight per unit volume. and this gamma is equal to W over V. Now we know that the unit of weight is Newton, while the unit of volume in SI system is cubic meter. And we also know that weight is the force with which Earth attracts a body toward its center, and this weight is equal to W is equal to mg. So if we put the weight is equal to mg in this equation, so it will be mg over volume. And from our previous knowledge about density, we know that density is equal to mass per unit volume. So if you replace this mass per unit volume with density, so what we will get is that we will get this specific weight gamma is equal to rho into g. So this weight density can be also defined as it is the product of mass density or density multiplied by g, which is acceleration due to gravity. Okay, so if you know the density of material, and you can calculate its weight density. The third property of the liquid is specific gravity, or it is also known as relative density, and it is represented as S. Now relative density means we are going to compare the density of two fluids, and that is also specific gravity. So whenever you are going to compare any fluid with respect to another fluid, so there should be a reference fluid or standard fluid to which we can compare its density. So based on the basis of this, we can define specific gravity S is equal to density of fluid which you are going to measure divided by density of standard fluid. Now this standard fluid should be at standard temperature and pressure, because changing at any other temperature or pressure, the standard fluid will also having different properties. So at STP, we will take this fluid and we will compare the density of fluid which we want to measure. So this is what we call specific gravity. Now for liquid specific gravity Sg is defined as density of liquid divided by density of water at 4 degree centigrade. So for water, the standard for density of liquid, the standard fluid is taken as water. So this specific gravity will be equal to density of liquid which you are going to measure divided by density of water at 4 degree centigrade. And for gases, we can define specific gravity for gases as well. That will be equal to density of gas divided by density of air at STP. Here the gases are compared with the density of air. Clear? So I hope this specific gravity you will have a clear understanding about this specific gravity. Now you have to memorize these two things, that density of water is equal to 1000 kilogram per cubic meter, while density of air is 1.21 kilogram per cubic meter. Both are at STP, standard temperature and pressure. So we will use these above values to calculate the specific gravity of fluids. Where this specific gravity will be used, or what are the uses of specific gravity in problems. So for that we will look into a simple problem, and the problem statement is that if you have been given unknown fluid with specific gravity is equal to 13.6, clear, and we have been asked to find the density of this fluid, density of this unknown fluid, clear. So how you will find this density? So again, by definition, that specific gravity is equal to density of unknown fluid divided by density of water at 4 degree centigrade or standard temperature and pressure. So here we have been given specific gravity 13.6 is equal to density of unknown fluid, clear, divided by density of water at 4 degree centigrade is 1000 kilogram per cubic meter. So from here the density of unknown fluid will be equal to 13.6 into 1000 kilogram per cubic meter, and we will get 13600 kilogram per cubic meter, clear. So this will be the density of unknown fluid. What does this means? That again, from this specific gravity we can say that the density of unknown fluid is 13.6 times greater than or 13.6 times the density of water. So in this way we can calculate the density of unknown fluids. Now we will discuss the some of example of surface tension in different cases. So we will discuss water droplet, soap bubble and water jet. So starting from water droplet. Let's take a droplet of water that is in spherical in shape, and the radius of this droplet is represented by R. The spherical shape of the droplet is due to the surface tension, and the molecule inside this droplet are closely packed due to cohesive forces. As a result, internal pressure P is greater than outside pressure, which is maintaining this spherical shape. So if you cut the half of this droplet, clear, and draw its diagram, so it will look like this. So this will be the radius of this droplet. There will be inside pressure which will be equal to Pi. Over the surface there will be a surface tension which will be represented as sigma, and that will be acting on the circumference, clear. So the inner pressure will produce force which will be equal to P multiplied by this cross-sectional area. So this cross-sectional area is represented as pi r square, and that should be equal to this sigma, which is the force per unit length into circumference 2 pi r. So from here we will find this internal pressure P that is required to maintain this spherical shape over pi r square. So pi will cancel and r will cancel, and we will get 2 pi over r, clear. And this is the inside pressure that is needed in order to maintain this spherical shape of the water droplet. So if you know this surface tension and radius of droplet, so you can find the internal pressure for the droplet to maintain its shape. Next we will discuss the soap bubble. So again, if you take the soap bubble, it will be also acting like a spherical in shape having radius r, clear, and having internal pressure P and outer pressure as P naught. Now you can see that this bubble is empty inside this bubble. Clear? So there will be two free surface, one on this surface and another one will be this surface. So I will write number of free surface in soap bubbles is equal to 2. So what if you again if you take the cross section or half portion of this soap bubble, so you can see that this will be the radius of this bubble. Clear? And that will be the internal pressure Pi. Clear? And there will be a surface tension over this circumference both in inside and outside. So in this case, force that is acting toward the right will be P multiplied by projected area. So this will be the projected area, which will be equal to pi r square, and that will be equal to, here we have two free surface, so 2 multiplied by sigma multiplied by circumference, which is 2 pi r. So from here we will get P is equal to 4 times sigma pi r over pi r square. So pi will cancel, so we will get 4 sigma over r. Clear? And this will be the internal pressure that is needed in order to maintain the shape of the soap bubble. The third case that we will discuss will be water jet. So if you have noticed that water jet is in the form of cylindrical shape, so for analysis we will take this as cylindrical shape. So this is the cylindrical shape of this jet. So inside pressure will be Pi and outside pressure will be P naught, and this Pi will be equal to P, which is the inside pressure. So here you can see that there is the only outer surface which is the free surface. So free surface is equal to 1. Clear? So in this condition, if you take the half of this cylindrical shape, so it will be like this. Let me draw it first. It will be like this is the cylindrical surface. Clear? And the pressure that is acting in the inside pressure is P, and due to this surface tension, this will be the sigma. Clear? This will be the sigma, which will cause this to contract. Clear? Let the length of this jet which we are going to analyze is L. Clear? And let this is the radius of this jet. So again, the force that is acting toward this left side must be equal to the force toward right, net force toward the right side, in order to maintain this cylindrical water jet. So I will write force towards left will be P into this is the projected area. So you can see this is R, so this will be R. So 2R multiplied by length. This will be the projected area over which this internal pressure is applied, will give you the force. So P into 2R multiplied by L is equal to sigma multiplied by L 2L. Why 2L? Because you can see one length is this and one length is this over which it is acting. So we can write this as 2PRL is equal to 2 sigma L, and P will be equal to 2 sigma L over 2RL. LL will cancel each other and 2 will also cancel each other. So P inside pressure will be equal to sigma over R. So if you know the surface tension for the fluid and the radius of this cylindrical jet, so you can find this internal pressure P in order to maintain this cylindrical jet. Our next topic is type of forces in fluids. So I will write it, type of forces in fluid. So we have two type of forces in fluid. The first one is adhesive force and the second one is cohesive force. Now what is the difference between these two? So first one is defined as the force of attraction between liquid with a solid is known as is adhesive force, and the second one is the force of attraction, the force of attraction between the molecules of same liquid is known as cohesive force. Now what does it mean? For that I will take a container, that is, this is the container, clear, and this container contains a liquid, clear, that this is the liquid portion. Now if you look at this, so this is the region which is known as solid liquid interface. So solid liquid interface. At this interface, the force of attraction between this solid surface and the molecule will occur, and as a result adhesive force will be generated. That is why adhesive forces are known as surface forces, surface force, clear. On other hand, there are various molecules in these liquids which are continuously interacting with each other. Either they are attracting each other or repelling each other. So as a result of this interaction, there will be a force of attraction or repulsion in between these. So these are known as cohesive forces. So I will summarize it. Adhesion force is the force acting between two surfaces or between the molecule of two surfaces. So adhesion is surface force. Due to adhesion, this liquid, due to adhesive force, this liquid adhere or sticks to the wall of this container, and due to this cohesive forces the molecule attract each other, so as a result they become denser. So these are the two type of forces that occurs in this fluid. Now based on this, based on type of forces, type of forces in fluid, we divide fluid into two categories. The first one is wetting fluid, clear, and the second one is non-wetting fluid. Now what is the wetting fluid? So for that I will write the first one. If your adhesive force, clear, if your adhesive force is greater than cohesive force, then liquid or fluid is said to be wetting fluid, wetting fluid or wetting liquid. And the second condition is that if your cohesive force is greater than adhesive force, then liquid is non-wetting liquid. So in this case, the molecule will attract each other intensively and try to condense. For example, the example of this is coal tar, grease oil, and the one most important is mercury in thermometer. So you have seen that there is no sticking action between the wall of thermometer and mercury. Clear? So these are non wetting liquids. On other hand, water on surface of glass is the example of wetting liquid. Now we will discuss some other criteria for wetting liquid and for non-wetting liquid. So I will write first for wetting liquid. So for wetting liquid, we will take the example of water glass interface. Clear? So if you put water on a glass interface, like this is the glass interface, and you put water on it, so due to adhesive force is greater than cohesive force, this water will expand over this surface. Clear? So how we will observe whether this water is a wetting liquid or not wetting liquid. So we will analyze this droplet of water on this water glass interface. So what we will do is that we will draw a tangent to the liquid where it makes a contact. So you can see the liquid made contacts over here. So if you draw a tangent to this contact point on this water glass interface, so it will make an angle with this horizontal surface, and this angle is known as theta, and this theta is known as angle of contact. Clear? Now the criteria is that if angle of contact, if this theta angle of contact is less than 90 degree or pi by 2 radian. Clear? So this liquid is wetting liquid. Wetting liquid. For non-wetting liquid, the cohesive force, I will write it for non-wetting liquid. The cohesive force will be greater than the adhesive force, so the liquid will try to contract and it will take the shape like this, as spherical shape which I have drawn over here. Let this is in contact with some other surface as shown in the figure. So you can see that this is the point of contact which is with this surface. So if you draw a tangent to this surface, it will be like this. So now the contact angle will be the angle between this tangent line and the horizontal surface will be this theta. And this theta you can see is greater than 90 degree. Clear? So theta is greater than 90 degree or pi by 2 radian. So we can say that this liquid is non-wetting liquid. It will not stick to the wall of this interface. Clear? Another property of fluid is capillarity. So what is capillarity? So by capillarity, we means the phenomena of rise or fall of a liquid surface in a small tube relative to adjacent level of liquid. when tube is held vertically. What does it mean? So let's explain it. Clear? So let we have a container. Clear? This is the container containing the fluid. Clear? And when you insert a tube in this container that is held vertically, so the liquid fluid from this container will try to enter this tube and will flow upward. Clear? So in your as per your understanding, it should match the level of this fluid in the container, but this does not happen. Either this level of water or fluid in this tube will rise or it will be down. So this is known as capillarity, the phenomena of rise or fall of a liquid surface in a small tube relative to adjacent level of liquid when tube is held vertically. The liquid start moving into the tube and we think that it will reach to the existing level as in container, but this does not happen. Thus the liquid will either go upward or downward. So what will happen if you take this container, clear, and you place this tube in that and let this is the level of this is the fluid in this container. So due to this, if the level in this tube go upward, so this difference between these two levels is known as H, and that is known as capillary rise. On other hand, it might go downward. This level may go downward, just like in this example. So now this is the level of fluid and this is the level in this tube. So this will be also known as H. Clear? And this is known as capillary depression. So either there will be capillary rise or there will be a capillary depression. So what are the reasons for this capillarity? So due to adhesion and cohesion, this capillary rise and capillary depression occur. So if you have for capillary rise, the adhesive forces will be greater than cohesive forces. Clear? So you will get rise or capillary rise in this tube. And for cohesive forces greater than adhesive forces, there will be a depression or fall in this level in this tube. Another term you can say that for wetting liquid will tend to cause capillary rise, and non-wetting liquid will cause capillary depression. Now what will be the formula for capillary rise or fall? So we will talk about that formula for finding capillary rise or fall. So this capillary rise or fall is equal to H, and this H is equal to 4 times sigma cos of theta divided by rho g into d, where this rho is equal to surface tension, theta is angle of contact, rho is density or mass density, g is acceleration due to gravity, and d is diameter of tube. So if you know all these values, you can find the capillary rise or fall in the level of liquid. This capillarity depends on diameter of tube, and it is independent of size of the vessel. Now in this equation we have theta, which is the angle of contact, and how you will find this angle of contact. So let's analyze this. Let's take a container, clear, having fluid, and there is a vertical tube, clear. This is the tube having diameter d, and this is the level of fluid in the container. So due to this fluid, the fluid will rise in this tube, clear. Let we take that this is wetting fluid and there is a rise in this level, and let we take this as concave shape. So this is H, which is the rise. Now this surface can be concave or convex, but here we will take this concave surface and we will analyze it. Now the surface, this concave surface which is formed in this tube is known as meniscus. So I will write it here, meniscus, clear. Let the radius of this meniscus is r. So let this is concave in shape or semi-spherical, so it have radius r, clear. This is the capital radius, and this is the radius, small r is the radius of this tube. So I will write it here. The small r is the radius of tube and this capital R is the radius of this meniscus. So in order to find the angle of contact, so what we will do is that we will draw a line tangent to the point that is joining, that is obtained by joining this the center of meniscus to the perpendicular of this point, clear. If you take the perpendicular of this point and draw a line that is tangent to this surface, clear. Now the angle that is made between this wall of this tube with this tangent line will be equal to theta, and this theta is angle of contact. So theta is equal to angle of contact, and it is the angle between tangent line and the tube wall will be the angle of contact. So this is how we can find this angle of contact for this capillary tube. So you may also solve many problems related to capillary tube by using this formula. H is equal to 4 times sigma cos of theta divided by rho g into d, where you will be given all values, but in some cases you might not be given theta value. So for this, for the condition or for the case for clean glass water interface, clear, this theta angle will be equal to 0 degree, and this will be the case of capillary rise. So you have to memorize this thing. And for mercury glass interface, this theta will be equal to 128 degree, clear, and that will be for capillary depression. Now the last topic in this lecture will be annular capillarity. So what is this? So the rise or fall in annular tube will be known as annular capillarity. So this will be explained by the same manner that we discussed the capillarity. So you have container and you have annular tube. What is annular tube? Annular tube is hollow tube with a solid portion or solid rod in between this hollow portion. So this portion is solid portion, clear, and let this is the center. So this will be equal to R2, clear, and this portion will be equal to R1, clear. And there is a liquid or fluid in this container. So due to this capillarity, the liquid will move in this hollow portion and it will tend to raise the level in this annular tube. Let this level is like represented like this. The meniscus is shown over here. So this will be the rise, capillarity rise in this annular tube. So in order to find this capillarity rise or fall is this annular capillarity, we have formula 2 sigma into cos of theta divided by rho g into R2 minus R1, clear. So theta is contact angle, sigma is surface tension, rho is density, and g is acceleration due to gravity. R2 is the outer radius and R1 is the inner radius of this annular tube. And this theta can be measured in the same manner as we did in the capillary tube. Later on we will solve different problem related to this capillarity, and I hope you have enjoyed this video and you are learning from this as well. Thank you.